Hi, welcome back. For the last 2 weeks, we have been talking about waves. The first week, we learned the basics of waves and some of the equations to go with it. Last week, we focused on sound waves, how they travel, how temperature and medium affects them. And this week, we're going to specifically learn about radio waves. All right, so first thing, you have to think back to 9th grade, that electromagnetic spectrum. Okay, the electromagnetic spectrum has a wide variety of waves on it. It starts over here with radio waves, microwaves, infrared, that's like heat, visible, this is the area that we can actually see, so that Roy G. Biv, the colors of the wavelengths that our eyes can pick up. And then as we move into higher energy, we have ultraviolet rays from the sun, X-rays, and gamma rays. We are going to focus over here on this column of the electromagnetic spectrum. The key things to remember about all of these types of waves, all electromagnetic, that's how we abbreviated EM waves, travel at the speed of light. The speed of light, it is on your equation sheet, it is 3 times 10 to the 8th meters per second. The other thing is they do not need a medium to travel through. You do not have to have air molecules, you do not have to have a solid, a liquid, or a gas. They can travel through empty space, which is how light makes its way from the sun to the earth. All right, radio waves are the same way. Looking at the electromagnetic spectrum, this side where radio waves fall, these are the ones that have a really long wavelength. Some of these wavelengths are going to be hundreds of meters long. Because frequency and wavelength have an inverse relationship, the longer the wave, the less times it comes, the lower the frequency. If you move all the way to the other end of the spectrum, over in gamma rays, these are super high energy waves. They have a very short wavelength. They're tiny, 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 which means they have a very high frequency. There is a lot of waves per second because each of them is so small. All right, specifically radio. It is a method of transmitting electrical energy from one place to another. It's sent by a transmitter and it's picked up by a receiver. Okay? In AM broadcasting, the amplitude of the carrier wave is modulated, that means changed or modified, to encode the original sound. So in AM radio, they change or modify the amplitude of the wave. A reminder, amplitude is how high, up and down. Okay, in FM broadcasting, the frequency, F stands for frequency, of the carrier wave is modulated. That's how many waves come per second, the frequency, to encode the sound. It is then broadcast out at a particular frequency. Each radio station gets its own frequency. It broadcasts out its signal. A radio receiver extracts the original program sound from the modulated radio signal and turns it into what you hear. So the receiver takes it, turns it back into what it was originally sent out as. Okay, so looking at the basics of AM and FM radio. Radio waves travel at the speed of light. So we have to know that V is 3 times 10 to the 8th meters per second. So this is always a given. Every single time when you're talking about radio waves, or light waves, or microwaves, any of those types of things on the electromagnetic spectrum, the V is always a given. It is 3 times 10 to the 8th meters per second. Specifically for FM radio, FM, F stands for frequency, and the M stands for modulation. So what that means is when they send out a FM radio wave, they are changing, modulating, modifying the frequency of the wave as it gets sent out. FM radio stations, they take a certain place on the dial. They are broadcast in megahertz. A lot of your radios, if you look at it in your car, it'll say MHZ. A megahertz is MHZ. It is equal to 10 to the 6th, a million hertz. Okay, that number right there is on your equation sheet underneath the speed of light. Okay, so what that means is, whatever radio station you're listening to, so let's say you're listening to KDWB 101.3, Okay, the 101.3 is actually telling you the frequency at which the waves are being broadcast at. Okay, so the frequency for 101.3 is 101.3, and then we have to put it into hertz times 10 to the 6th hertz. Okay, so this number is sent out in megahertz, which is 10 to the 6th hertz. So all you have to do for any FM radio station, whatever the call numbers are, the 101.3, you just behind it write times 10 to the 6th, that converts it into hertz. We need that in order to do our math. All right, so an example for FM, calculate the frequency and wavelength for K102.1. All right, so first thing, we always know the speed of any radio wave is 3 times 10 to the 8th meters per second. Okay, the other thing that we know is the frequency is equal to the call numbers, 102.1, times 10 to the 6th hertz. We got to change it from megahertz to hertz by putting times 10 to the 6th behind it. So that is this with 6 more zeros behind it. All right, so we have already done one of them. The frequency, we have already converted it to hertz, so it is 102.1 times 10 to the 6th hertz. You could certainly move your decimal place if you wanted to get it behind the first number, but you don't have to. Okay, to calculate the wavelength, we have to use our old wave equation. V equals frequency times wavelength. We now just plug things in. V is 3 times 10 to the 8th is equal to the frequency, 102.1 times 10 to the 6th, you can't leave that out, times the wavelength. We want the wavelength alone, which means this has to divide under. Okay, when you use something with exponents and divide it under, you have to put it in parentheses. So when you take 3 times 10 to the 8th divided by, in parentheses, 102.1 times 10 to the 6th, you should get a wavelength of 2.94 meters. All right, which means that wave is about the size of the front of my room. It's pretty big for a wave. All right, so that if we could see radio waves, we would see a very large wave coming at us. All right, let's move on to AM radio waves. How are they different? Well, AM stands for amplitude modulation. Amplitude modulation. Which means as they change the wave in order to get it to transmit, they change the amplitude. So it'll have a wave that's big and then small and then big and then small. Okay, they then have a specific frequency that they have to transmit it on, because otherwise all the waves would run into each other. It has to go at a specific frequency. The AM stations, they are not broadcast in megahertz, they are broadcast in kilohertz, which is abbreviated KHZ. Okay, instead of being 10 to the 6th, this is 10 to the 3rd. So it gets 3 more zeros behind it. All right, so let's say you listen to AM 1130. Okay, that right there, what it's being broadcast at is 1130 kilohertz, but we have to have it in regular hertz. So we take the 1130 and we just go times 10 to the 3rd behind it to change it into hertz in order to get it into its regular unit. Okay, so the main difference is FM is frequency modulation. When they send out their wave, they modify the frequency. They have waves that are close together and farther apart. Whereas AM stands for amplitude modulation. It's the height of the wave that they're changing as they send it out. They then have a specific frequency for each radio station, so they don't run into each other. They have to be far enough apart. FM gets sent out in megahertz, which is 10 to the 6th hertz. AM gets sent out in kilohertz, which is 10 to the 3rd, or 1,000 hertz. All right, to do our math behind AM, calculate the frequency and wavelength for AM 1500. Okay, first thing, we know that the velocity of all radio waves is 3 times 10 to the 8th meters per second. So that has not changed, that stays the same way. Okay, for the frequency, it is AM 1500. Which means the frequency is going to be 1500, That's kilohertz. I gotta change that into regular hertz by putting times 10 to the third hertz behind it. Or you could just add 3 more zeros if you prefer to do it that way. But it's the same as multiplying it by 10 to the third. All right, so I already know my frequency. I changed kilohertz to hertz, so it is 1500 times 10 to the third hertz. You could also write it as 1500 with 3 more zeros behind it. Those numbers are exactly the same thing. The 10 to the third is 3 more zeros. All right, calculate the wavelength. Okay, so I need to now use my equation, V equals frequency times wavelength, and I'm going to calculate my wavelength for an AM radio station wave. Okay, the V is still the same. 3 times 10 to the 8th equals my frequency, 1500 times 10 to the third times the wavelength. I want to find the wavelength, which means I need to divide this over. Once again, this has to go in parentheses if you type in the 10 to the third. Otherwise, your calculator does its order of operations incorrectly and you get a wrong exponent. Okay, so check your calculator, make sure you have done it correctly. When you take 3 times 10 to the 8th and divide it by 1500 times 10 to the third, you should get 200 meters. Think of how long that wave is. I mean, that would be like 2 football fields. That's how long that type of a radio wave is coming from an AM radio station. All right, 2 last questions to kind of sort these things out. Do you think AM or FM works better for music, and why? Well, in order to have music, you have a lot of pitches, and different pitches have different frequencies. The higher the pitch, the higher the frequency, lower the pitch, the lower the frequency. Okay, AM is amplitude modulation, FM is frequency modulation. Okay, you should know that FM works better for music because obviously that's where all the music stations are. But the reason is it has more frequencies, which is better for music because more frequencies means more pitches. If you've got high notes and low notes in your music, then they're going to put it on an FM radio station because it will cover more frequencies. AM radio stations are used more for just talk, and where you don't change the pitch as much as you do in music. And then finally, why can't we see radio waves? Think about it. These things are between 2 and 200 meters long. They are humongous. Why can't we see them? Okay, it goes back to this right here. Visible light to human eyes is only in this little part of the spectrum. There is a wavelength associated with visible light. It's like in the 300 to 750 times 10 to the negative 7 meters for the wavelength. If it's outside that, our eye receptors don't pick it up. They just can't see them. All right, so it doesn't fall into our the receptors that our eyes can pick up. So frequencies are not ones that our eyes can pick up. They're not receptive to it. The receptors in our eyes, the rods and the cones, they don't vibrate unless it's within that particular wavelength, and radio waves don't do it for them. Okay, so they can't see radio waves. Okay, moving ahead, we are going to do a chunk of these together. So looking at the radio problems, the first 5, you should know these off the top of the notes up there. The speed of light, if you forget it, it is on your equation sheet. It is 3 times 10 to the 8th. Radio waves travel at what speed? The speed of light. So you can either write light or 3 times 10 to the 8th. Either one will work. Here's a good question. Which travels faster, sound or light? Okay, we know that light is 3 times 10 to the 8th. Sound, thinking back to last week, was more like 330 meters per second. The answer is light. About 1,000,000 times faster. So much faster. And that's because it doesn't need a medium to travel, whereas sound does. It takes time for it to travel. Okay, That is why you see lightning before you hear the thunder. The light comes, but it takes the sound time to travel the distance to where you are. Okay, so light is like 1,000,000 times faster than sound. AM radio waves are broadcast in kilohertz. KHZ is how you abbreviate it. FM is broadcast in megahertz. MHz. Looking at, those next bunch you can kind of do together. We are going to do 10 and 11, kind of walk through those. One of them is just like our example in the notes up above. So we're going to start with number 11. Calculate the wavelength from the signal from 101.3 kDWB. All right, so we know that radio waves travel at the speed of light. So automatically you always get to put V equals 3 times 10 to the 8th. We also know that the frequency is a given. It is whatever the call numbers are, 101.3, but that's in megahertz. So I got to change it to hertz. So I need times 10 to the 6th. Because it's FM, it's 10 to the 6th. If it was AM, it would be 10 to the 3rd. All right, I am then going to take this. I want to find wavelength. The only equation I have to calculate wavelength is V equals frequency times wavelength. You are going to plug those in. You're going to divide the frequency over, and you are going to come up with a wavelength for me. Okay? So you just have to plug in your two numbers and plug it in. For number 10, what is the period of a wave from 101.3 kDWB? Okay, remember period. The equation for period is 1 over the frequency. Okay, we have the frequency right here. So I just need to take 1 divided by, use parentheses when you divide by an exponent, 101.3 times 10 to the 6th. And when I do that, I am dividing by a big number, which means I'm going to have a very small number. It is going to come out as 9.87 times 10 to the negative 9 seconds. Or if you put that in a regular number, it means move your decimal place 9 spots over, so it would be Alright, it is a very small portion of a second. Does not take much time for the period, for one wave of a radio wave to pass. It doesn't take much time. The other one I want you to look at is number 13. So how many seconds would it take a radio wave to travel 2.2 miles? Okay, so I know the distance. Delta X is 2.2 miles. But I can't leave it in miles. I have to change it to meters. So you have to convert 1609 meters in a mile. So you're going to have to change the miles into meters by multiplying by 1609. Okay, a radio wave, we know that the velocity is always 3 times 10 to the 8th meters per second. So you're going to have a distance, you're going to have a velocity. If you want to solve a time, we know that all waves move at a constant speed, so you are going to be able to use that equation right there. All right, I think those are the ones I wanted to cover with you, just reminding when you need to convert and that type of thing. So don't forget to get to class this week. There is a quiz online. You have to be on Zoom in order to get points for the quiz. So thank you very much. Have a good week.